Okay, my people, how are we doing today? We're going to go ahead and get started on the chain rule, which, if I'm not mistaken, is 3.4 in your book. Now, this is sort of a logical conclusion of all the rules that you've been learning. In the first section, you'll learn the wonderfully underwhelming rule that when you deal with a sum or a difference function, that you can go ahead and do the derivative term by term. Okay, and that was, like I said, very underwhelming, and you kind of wondered why you learned it. And then in the next section, you learned the product rule, right? And you learned, and this one was, of course, relatively easy because the order really didn't matter as long as you got one of the functions, the derivative in one, and the other one differentiated in the other. The next one, of course, was the quotient function. The quotient rule, and it was, just a little bit more difficult, but not incredibly so. Just as long as you remember that the bottom is the first thing that you initiate on the numerator of the rational expression that you're going to wind up with. And it winds up something like that, right? Now, what do all of these look like? Well, they all look like combination functions, and we actually spend a little bit more time than the average pre-cal and Algebra 2 class does on combination functions, because I think it's pretty helpful in terms of being able to understand what's going on in the function, to be able to understand it, how to relate it to graphing, especially vis-a-vis transformations, because if you think about it in the right way, it becomes just basically a logical extension of the logic of transformations, which of course we spent an incredible amount of time on. But when we talked about combination functions, that was a prelude to talking about composite functions. Now, the chain rule is the derivative of composite functions. And that's pretty important because composite functions are not when you're, joining functions by a known operation like addition, subtraction, multiplication, or division, but when you've taken one function and crammed it inside the other one. So when you've taken one function and crammed it inside the other one, how does that affect the derivative? And of course, you need to be able to look at the functions that are given and be able to see the layering of the composition. And you'll understand a little bit more about what that means when we actually get to examples. But the notation that goes along with the rule is this. And this will make a little bit more sense as we get going along in terms of examples. But this is when you have f of g of x, f being the sort of outer layer of that composite function, you want to take the derivative of the outer layer, f prime, leaving the inside alone. Notice that g of x is left alone. That g of x is identical to that g of x, okay? So you take the derivative of the outside, leaving the inside alone, and then multiply it by the derivative of the inside. And let's go ahead and do an example of that. Let's say we have h of x is equal to, I don't know. Let's go ahead and do something like, let's do 2x squared minus x to the third, okay? Now, the question is, what is the most outside thing that's being done here, okay? The most outside thing that's being done here is that cubing, okay? And when you're talking about the most outside thing, we're really talking about the last thing that is accomplished according to order of operations. So if you were to actually plug a number in for x, you would do all of this stuff inside the parentheses, exponent, multiplication, subtraction, and then the very last thing that you would do is you would cube it. So that tells you the outside most thing, and that is your f, of course. So if we have f is equal to x cubed, and g of x is equal to 2x squared minus x, okay, then we can basically define h of x as f of g of x, right? And remember, composition of functions is just an extension of function notation. What happens when I plug in a 2 right here? Well, I plug in a 2 for x. and it becomes 8. What happens when I plug in a 4 right there? I'll plug in a 4 right there, and it becomes 4 cubed, which is 64. What happens when I plug in a 2x squared minus x right there? Well, it becomes 2x squared minus x cubed, right? So if we can actually look at a function like this and be able, now you don't need to be doing this stuff. This doesn't need to go down on the paper, right? Except for maybe, you know, like your first day of sort of walking through examples to remind yourself about composite functions. This is what goes on in your head. But remember that once you've identified what's going on the outside, when you're taking the derivative of h, you're not really worried about the inside during that first little bit, because really that's just stuff cubed. I don't really care what the stuff is. That's stuff cubed, or that's something cubed, right? So what's the derivative of something or stuff cubed? It's 3 times stuff squared, right? It just so happens, in this case, that the stuff is 2x squared minus x. And now I need to deal with the inside. I need to deal with the derivative of the stuff. And of course that winds up, of course, since it's a polynomial, term by term, being 4x minus 1. Okay? So let's get a little more specific. This right here is your f prime of g of x. Okay? This right here is your g prime of x. You identified that inside function as g, right? Remember that when you take the derivative of the outside, you leave the inside alone. And that is exactly what you did here. That g of x, in this case being the 2x squared minus x, is identical to that g of x, right? The 2x squared minus x. So you've taken the derivative of the outside, leaving that inside portion alone. Stuff cubed became 3 stuff squared times the derivative of that stuff. Okay? And I've sort of belabored the point, and I want to go over it and over and over again. You know, first of all, because repetition is pedagogically advantageous, and second of all, because you haven't seen it since last spring. Okay? Well, let's go ahead and try and do as many examples as we can actually fit in a reasonable amount of time. Let's go ahead and look at y is equal to the cube root of negative 2x to the 4th plus 5. Okay? Well, you're like, wow, that's a radical. I don't know about the radical. Radicals always screw me up. Well, the great thing about radicals is we learned how to deal with them as exponents, because radicals are fractional exponents. Now, I don't care whether you do this in your head or whether you actually show it on paper, but this is expressible as this, okay? And of course, the most outside thing that's going on is the stuff to the 1/3. I don't care what the stuff is right now, initially. That's stuff to the 1/3 power. So when I have dy dx, or y prime, whichever is your habit of doing, I need to bring down 1/3 stuff to the negative 2/3, and only now do I really care about what that stuff is. I now need to take the derivative of that stuff. Now, that is the derivative of y. Okay? Now, what do you think is the most common mistake when dealing with problems of this variety? Because this is actually a special case of the chain rule called the general power rule, or the generalized power rule. And if you hear general power rule, all you really need to think is, oh, that's just a specific instance. That's a specific kind of chain rule problem, because that's really all it is. But notice that it actually mimics the power rule that we did. The power rule was simply the derivative of x to the n becomes n x to the n minus 1, right? Well, the general power rule is some function u of x, right, is n times u to the n minus 1 times u prime, okay? So that's the power rule. That's the general power rule when you're doing it with u, where u is understood to be some function of x. In this case, your u would be, you know, what we talked about in terms of the chain rule is your g of x, that inside portion right there. Notice that these are just formalized ways of just doing what I'm trying to explain in terms of just the you know, the general chain rule idea of basically looking at it as a composite function and trying to take the derivative of the outside, leaving the inside alone, and then, and only then, taking the derivative of the inside. Now, this type of problem right here, there is a very specific mistake that I see most often. And that specific mistake is this. You're so worried about getting to this port right here and actually taking the derivative of that inside and doing it correctly that you forget to put the new exponent up there. And I see it all the time, okay? Not all of you will be susceptible to that mistake, but a good number of you will be. You know, after you bring the 1/3 down, you need to you know, subtract 1 from the 1/3. That's why we get the negative 2/3 right here. But I don't know how many times I've, on a test, seen that negative 2/3 or whatever the n minus 1 is not show up. Okay, so be very, very careful about that in terms of sort of being on the lookout for common mistakes, and I like to warn you guys about those ahead of time. Now, let's go ahead and do one that's a little bit more difficult. This one, of course, is a little bit more difficult because it's going to involve other things besides just the chain rule. And this is, let's do it negative 4x squared minus 3. Okay? Now, notice that if it were just this, okay, that would be the chain rule. If it were just that, that would be the chain rule. But it's the product of both of them, okay? Now, when a larger problem like this, the thing that you have to figure out is, okay, what is the largest thing that's going on? What is the biggest thing going on? And of course, at that point, in order to answer that question, you run right back to order of operations. In terms of order of operations, what is the last thing that's going to go on here if I were to actually plug a number in for x? And the answer is the product. The product of this right here and this right here, okay? So if the product is the last thing, then the product is the biggest thing going on in this particular problem. And if that's the case, then your chain rule stuff is going to be sort of embedded within the larger context of a product rule question. Now let's call this U, and let's call this V, right? Well, because, you know, we talked about F and G, but of course, you know, you can also formalize, and some books do, when you're taking the derivative of a product. They call it U and V so that they can shorthand it like that, right? And therefore you don't have to do the of x, and you can sort of dispense with the function notation stuff. So that is another way of expressing, in terms of notation, the product rule. So we're going to call it U and V, and we're going to go ahead and take the derivative, knowing that it's going to be a product rule problem. Now let's go ahead and let's go ahead and stick with this formula right here. Let's do U first, even though, you know, you could mix up the order of these as long as it's, you know, legal according to the commutative property. It could be V prime U, right? You know, plus VU prime, because multiplication is commutative. You could take this term and put it first, so it could be U prime times V plus U times V prime. But just to keep with this, so it's very, very straightforward, let's actually do it in this particular order. So I want U, so I just need to reproduce this factor right here. Okay, and then I need V prime. Well, V prime, of course, when I look at this, I need to see the 1/2 power. So that's negative 4x squared minus 3 to the 1/2 power. So 1/2 negative 4x squared minus 3 to the, and then negative 8x, okay? But we need to be very careful to make sure that you have that negative 1/2 power right there, okay? Notice how I went back to do it. And I was trying to emphasize the fact that how easy it is just to write this and go straight to the negative 8x and forget that negative 1/2. Now this next one needs to be U prime, so that winds up being 5x cubed minus 3 to the 4th. times 15x squared times, and sorry, I'm going to have to write the v down here, negative 4x squared minus 3 to the 1/2. Okay, now that basically winds up being, here is your u, this is your v prime, this right here is your u prime, and this right here is your v. Now, I'm not going to simplify this. I'm not going to go ahead and clean this up because, you know, it'll take too much time to actually do that, and that's the algebra of it. And you're going to have to ask your teacher in terms of exactly how she wants you to simplify that. I'm less of a stickler about simplification of these than a lot of other teachers are, but I don't want to speak for her. But this is the calculus of it. The simplification, of course, would just be arithmetic and algebra. So as long as we understand why this is the way that it is, I think we're okay in terms of the calculus of it. Now, I'm going to go ahead and end this video, and I've been going through these first couple of examples really slowly, making sure I try and predict a lot of the questions that are going to come back around as you're being reintroduced to the chain rule. When we get to videos 2 through however many I wind up doing, I'm going to go just a little bit faster because hopefully you'll have gotten this under your belt. If you have any questions, of course, go ahead and email me. I'd be happy to give you some feedback. But if you're understanding that, I guess go ahead and click on video number 2 and keep going. Bye.